I'm going to talk about solving a system of linear equations, maybe using something slightly more sophisticated than our mere ninth-grade algebra techniques. So here are two examples of system equations. Here I've got two linear equations and two unknowns. Here are three linear equations and three unknowns. Geometrically speaking, to solve a system of two linear equations and two unknowns really amounts to, as a geometric consequence, trying to find the point of intersection between the two lines whose equations are given. Now, given two lines on a plane, I can either intersect at a single point, I can have parallel lines, or I can have coincident lines. The two lines are the same lines. So I could have, in the parallel situation, 0 points of intersection. Maybe in this situation, 1 point of intersection. The two lines can intersect at a point, or infinitely many points of intersection. In other words, the system, algebraically speaking, can have 0 solutions, 1 solution, or infinitely many solutions. Now, when it comes to a linear equation in three unknowns, that does not represent a line in three space. We're going to have to start talking about vector theory or vector calculus, actually, to get to that point. Instead, what an equation of the form ax plus by plus cz is equal to d, that equation represents, geometrically speaking, a plane in three space. Only three variables for that. I'm going to make the assumption you have seen that before. I can't tell you why this equation is plane yet. I've got to talk about a dot product prior to discussing that. But if we could just, at this stage of the game, understand that an equation is formed where x, y, and z are variables, a, b, c, and d are mere real numbers. They could be 0. That represents a linear equation in three unknowns, and geometrically speaking, represents a plane. So the planes can have 1 point of intersection. Say, here's a plane, here's a second, here's a third. Oh, sorry, I misspoke. First plane, second plane, third plane. There's only 1 point of intersection. There could be infinitely many points of intersection. They could all intersect at a line, or maybe they're all on top of each other and intersect with a plane. In other words, the three planes are the same plane. Or maybe they're parallel to each other, as an example, having no point of intersection. So just like a linear equation of two unknowns, with a system of three linear equations, three unknowns, I'm either going to have 0 solutions, 1 solution, or infinitely many solutions. Now, you've already studied back in ninth grade algebra 2 techniques to solve such systems. One of the techniques was referred to as a substitution technique. I'm not going to discuss that today. Your other technique was called, actually, I don't know what it's called. Some is called it the elimination method, some is called it the addition method. So that was the second technique you learned back in ninth grade algebra to solve such system equations. Well, I should say system of linear equations. What I want to do today is talk about a whole new technique. This technique is referred to sometimes as Gauss-Jordan elimination. Oh, I should spell that, shouldn't I? Or some to refer to as just rewriting the system as a single augmented matrix and reducing that matrix. Now, when I use the word matrix, it has a very, very easy definition. It's simply a rectangular array of numbers. And so I'm going to use what I refer to as an augmented matrix. I'll tell you why I've got the adjective augmented in a moment, to solve this system of two linear equations and two unknowns. Here's what I do. This technique basically is a gimmick. It just allows you to suppress viewing x's and y's. And so for me, this is not really a true application of matrices, because it's not really a true matrix in the way I look at things. But here I go. I'm just going to copy down my numbers. And I tend to put a vertical bar where the equal signs were, but that's just my notation. Now, notice what would happen if I had the ability to massage this matrix in some legal fashion and reduced it down to a matrix where I've got ones down the main diagonal, zeros everywhere else, to the left of that vertical line. Pound symbol and percent symbol are just two numbers. In rewriting this augmented matrix back in equation form, it would tell me that x is equal to pound symbol, and that y would be equal to percent symbol. So if I do have some tools in my back pocket that allows me to transform this augmented matrix into this one without changing the solutions to the original system given, then I will easily just be able to recite what my solution is. It's the order pair, where that's in the x coordinates position, that's in the y coordinates position. So let's talk about legal ways of massaging matrices. I refer to these as my elementary operations, and there's only 3 of them. take a peek at this equation right here. How about the one I started with? So, do you think, in multiplying both sides of the first equation by 3, changes my solutions? Because I think the answer is no. That just goes back to the addition property of equality, where it says if I've got that A is equal to B, then certainly, I think I just misspoke. This is just nothing more than the multiplication, not addition, property of equality. In other words, my solutions don't change when I multiply both sides by some non-zero fixed real number. So I think it's completely legal. But back in matrix form, doesn't that amount to just replacing one row with the multiple itself? So there's my first elementary operation. I can replace any row with a multiple of itself. Now, maybe I have no reason for multiplying both sides of that first equation by 3, but it's legal, and it doesn't change my solutions. Now, would you also agree that I can go ahead and rewrite the system as such? And not change the solution system? Because I think it's just interchanging these two equations doesn't change anything with the solutions to the system equations. So my second elementary operation. I can interchange any two rows. Excuse me. My goodness. So take a peek at this system of two equations and two unknowns. Now, one of those ninth grade algebra techniques is referred to as the elimination method. Please excuse me. Or maybe called the addition method. It basically says that I can go ahead and take, say, for example, the first row, multiply both sides by -2. I'll do it correctly. And add it to the row. And if I do, I completely eliminate the variable x. Now, if I divide both sides by -3, I solve for y. So this elimination technique basically says I can replace one of these equations with the sum itself and a multiple of another equation. That being the case, back in augmented matrix form, same thing applies. And this is my last elementary operation. We'll get started solving systems. So here I go. I can replace any row with the sum of itself and the multiple of another row. So those are my three elementary operations. And let's see, let's go back to the other board and solve the first system. So I have rewritten the system as an augmented matrix. And now let me just perform row reduction. Now to perform row reduction, I jump from column to column. Let's see if with this camera that I haven't used before, it shows color well enough. Looks good. So I'm going to plant my feet on the first column and identify which entry in the first column resides along the main diagonal. That'll be the 2. I'm going to force that to be a 1. When I'm done, I will force everything else in the first column to be a 0. Now, to get this first entry, the 2 to be a 1, what I'm going to do is multiply the first row by 1/2. And you know what? Now that it puts this in the board, I don't think it's positioned very well. Can I slide this over a little bit? I'm not going to change anything. I just didn't give myself much room. So 2, 3, 4, 5, 6, 7. Looks better. So planting my feet in the first column. Again, we're going to force the entry in the first column that resides in the main diagonal to be a 1, and everything else in that column to be a 0. So here we go. So to take care of the red action, let's you and I take 1/2 times the first row and replace or use it as my new first row. That'll force that entry to be a 1. And so I now have an equivalent augmented matrix whose entries are 1, 3/2, and 2. My second row doesn't change, at least not yet. So next on my list, I'm going to force that 5 to be a 0. And typically, not always, but typically when I want to force an entry to be a 0, I'm going to use the most previous row for which I created a leading 1. So here I go. To force this entry right here, that 5 to be a 0, let's multiply -5 to the first row, add it to the second row, and use the results of a new second row. So that means I correspondingly have, let's see, when I multiply the first row by -5, I'm only doing it in my head. I'm not officially at this stage of the game changing my first row, so I'm just going to copy it down. However, -5 times the first added to the second gives me -5 plus 5, which adds desired 0. Here I've got a -15/2 plus 12/2. Is that a -3/2? And let's see, -10 plus 7 is -3. So I'm finished with the first column. Now jumping over and planting my feet over the second column. I yet again want to identify the entry along the main diagonal in that second column and force it to be a 1. And when I'm done with that, I'll force everything else in that second column to be a 0. So here I go. Take care of the red action first. Piece of cake. I'm simply going to take the second row, multiply by -2/3, and use the result as my new second row. So let's see, is that going to give me this? So officially at this stage of the game, my first row still doesn't change. My second row becomes a 0, 1. Is that a +2? So in the second column, I force the entry along the main diagonal to be a 1. Now let me force everything else in the second column to be a 0. In other words, I need to transform the 3/2 to 0. To do that, I'll use the most previous row for which I created a 1. I should say the most previous row for which I created a leading 1. And that must mean I'm going to multiply -3/2 to the, whoops, I said -3/2 times the second row. Add to the first and use the results as a new first row. Officially, my second row doesn't change. It's just in my head, I multiply by -3/2, adding to the first. So give me this. That being the case, my solution is a set of a single order pair whose entries are -3 and 2. Or shall we say, geometrically speaking, the point of intersection of the two lines whose equations are given is at -3/2. There's only one point of intersection. So there's an example of using Gauss-Jordan elimination on an augmented matrix to solve a system of equations, in this case, 2 equations, 2 unknowns. I could also say that I rewrote the system as an augmented matrix and I completely reduced the matrix, meaning I forced the right-hand side to be of a special form. That special form is something I'm going to discuss in a few moments. Next on my list, well, that was too fast. Let's get more challenging with a system of 3 linear equations and 3 unknowns. Oh, I shook my board up a little bit. Let me double check, make sure it's still centered. Looks good enough. So everybody, here I go. I'm going to rewrite the system of 3 equations, 3 unknowns as a single augmented matrix whose entries are going to be 2, -1, 3, and 4. Excuse me, that's not a 4, it's a -1. 1, negative 1, excuse me, 1, 1, negative 1, 6. And let's see, 3, 2, 1, 9. And I just want to make sure I wrote down the right coefficients. So it looks good. Next on my list, I will use my matrix notation and include the augmentation. So I'm going to plant my feet on the first column, identify the entry in that one column along the main diagonal, and force it to be a 1. And I'll force everything else in that first column to be a 0. Now, to take care of the red action, I could simply replace this row with 1/2 times itself. In other words, multiply every entry by 1/2. There's nothing illegal about that. That's what I did in my last example. Notice, however, it creates fractions really fast. And so I think maybe an easier approach, just so I can avoid fractions for as long as I can. Maybe I'll just, how about interchange the first 2 rows? I think the corresponding equivalent augmented matrix is going to be this. Now I'll force everything else in the first column to be a 0. I can do that by, well, let me go back. To force this entry to be a 0, how about taking negative 2 times the first row, adding to the second, and using the results of a new second row. Let's also take the first row, multiplied by negative 3, add to the third row, and use the results of a new third row. That being the case, that means my first row, at least officially, doesn't change at this stage of the game. Negative 2 times the first plus the second gives me 0. Is that a negative 3? Oops, that's a lousy 0, sorry. Let's see, negative 2 times the first plus the second. Is that going to give me positive 5? Is that a negative 12 minus 1 is negative 13? But negative 3 times the first row added to the third row gives me 0. How about a negative 1? And let's see, I'll finish up the rest. So a 4 and finally a negative 9. So I finished my business with first column. Now it's time to jump to the second column. In the second column, I'm going to, number 1, force everything in the second column. Can I rephrase that? I'll force the only entry in that second column that resides on the main diagonal to be a 1. And I'll force everything else in that second column to be a 0. So in order to take that red action, how about if we just take negative 1/3 times the second row and use the results from our new second row? So is that going to give us this? So 1, 1, negative 1, 6. Is that a 0, 1, negative 5/3? Is that a 13/3? And my third row doesn't change yet. Now let's go ahead and force everything in that second column, everything else in that second column to be a 0. So to force this entry to be a 0, I'll use the most previous line for which I forced deleting 1 to exist. So how about multiplying negative 1 to the second row, adding to the first row, and use the result of the first row. To force this entry to be a 0, how about just straightforwardly adding row 2 to row 3? Use the results as our new third row. Now, is that going to give us a second row of something that doesn't change? So here I go. To take this action, does that give me the following? And adding the second and third rows together, does that give me the following?